Hello and welcome to our lesson on increasing and decreasing functions. So let's start by talking about what it means for a function to be increasing or decreasing. And these are terms you've probably heard of before, and I think we've even mentioned them so far in this class. But just to be safe, informally, if a function is increasing, it just means if we were reading it and we read from left to right, it means that the graph is going up. So we're going to say it's increasing if the graph is going up as we read it from left to right. So if we're going up from left to right, we're going to look something like this first picture here. So that entire graph in that first picture is increasing. It is moving up from left to right. Now, if we're going to be a little more formal, if we're reading left to right, that's our frame of reference. That means our x values are increasing. So from left to right on the x-axis, again, x values are increasing. If the graph is increasing, that means that as x increases, so do the y values. So if we're going to be a little more formal, a function's increasing. If a function is increasing, it means that as x increases, so is y. So as x increases, y increases as well. Okay, now if a function is increasing, it also means that it has a positive slope. So the slope of that line has to be positive. And slope, as we well know at this point, is a derivative, or derivative can be used to find the slope at any particular point on a curve. So if the function is increasing and its slope is positive, right, if the slope is positive means its derivative has to be positive too. So a positive slope on your function means your derivative is positive. That means your derivative is above the x-axis. So if the slope is positive, again, the derivative is going to be positive as well. Okay, and then similarly, if our function is decreasing, if it's decreasing, that means it's going to go down as we read it from left to right. So moving downward, left to right would be like this second graph we see here. Moving from left to right, that graph is continually decreasing. But again, if we're to be a little more formal about this, it means as x increases, so we're still reading from left to right, the y values are decreasing this time. Okay, so to be a little more formal, if our function is decreasing, that means as x increases, so that's always our frame of reference, we always read from left to right, this time the y values are decreasing, or as x, let's see. As x increases, decreases. I couldn't remember if I was es or ing. Okay, so again, if a function is decreasing, that means its slope is going to be negative. So if it's decreasing, the slope is negative, and slope being directly connected to our derivative means if the slope is negative, the derivative is going to be negative too. That means our derivative function would be below the x-axis. So the derivative would have to be negative if the slope was negative. Okay, and then what if our graph is neither increasing nor decreasing? So we'll see that in the next couple of pictures here. If we're not increasing or decreasing, it's a couple of things that could be happening. One, we might not have any function defined where we're looking, but if we are looking at where a function is defined, it could be that our function is constant, or it could be that our function is undefined. So we would have something happening like, again, in these next two pictures. So if I was reading this graph from left to right, we would say that this portion of the graph is decreasing until it gets to that turning point, and then when it turns, this portion of the graph is increasing. But this point right here where it actually turns isn't increasing or decreasing. So at every point along that green highlighted portion we're going to be decreasing. Every point along the yellow highlighted portion we're going to be increasing. But here we would have a horizontal tangent line, right? We would have a slope of 0. We would be constant there. So if our graph is constant, again, we're not increasing or decreasing, and that could happen at a turning point. So graphs or functions are going to be constant at turning points. And undefined over here. So if I'm looking at this next graph, so this all the graph we see is actually different behavior. I was going to say about to say the wrong thing. So this branch of the graph we would say is decreasing as we read from left to right. And then afterward here we see this graph is increasing if we continue to read from left to right. So we're decreasing and then we are increasing, but we have to separate those two intervals, again, not by a turning point here, but by something else. In this one, these two intervals are separated by a discontinuity. So there happens to be an asymptote in this graph. Let me go to pink here. So an asymptote in this graph separating these two intervals, just like the turning point separated the two intervals in the previous. So we could be constant if we're looking at a turning point, or we could be undefined if we're looking at an asymptote or some other discontinuity. So these discontinuities, these turning points, discontinuity, too much to spell and try to think and talk at the same time. These turning points and discontinuities are going to be places where we change from increasing to decreasing, or vice versa, or we just have to separate intervals because we don't have a continuous piece of graph. Okay, so if our graph is constant or undefined, what is happening is we have either a slope that is 0 or a slope that is undefined. So at this first one here, at this turning point, again I said that this slope would have to be 0 here, and at this discontinuity we have no graph defined, so our slope would be undefined. So here our slope would be 0, and here our slope is undefined. So if we have a piece of graph that is constant or undefined, that means again our slope is constant, our slope is 0 to be specific, and undefined. Okay, and so if its slope is going to be 0 or undefined, again the slope directly connects to our derivative. So if the slope is 0 or undefined, its derivative is going to be 0 or undefined. Alright, and just to be thorough here, so we said this entire piece of graph, this whole thing is going to be increasing over its entire domain. So if I said where is the increasing interval, you would say, well, this whole domain, everything from negative infinity to infinity is increasing. And similarly here, we said this entire graph is decreasing, so we would say this graph is decreasing over its entire domain from negative infinity to infinity. Now here, where we have that turning point, we have that slope of 0, we have a disconnect between our intervals, and in fact we're changing from decreasing to increasing. So in this one we're going to say it's decreasing over the domain negative infinity up to, let's see, where is this x value? This appears to be an x value of negative 3. Oh, I'm counting backwards, negative 2. So from negative infinity up to negative 2 it is decreasing, and then it turns and is increasing from negative 2 to positive infinity. So notice we're keeping parentheses on the negative 2 to exclude it, because again at negative 2 our slope is 0, but everything before that is decreasing and everything after that is increasing. Okay, and then similarly here we have an x value of positive 3, so that's like a separator between the two intervals. So the first interval is decreasing, we'd say this graph is decreasing from negative infinity up to positive 3, so that is the domain over which it is decreasing, and we would say it's increasing over the domain that goes from that 3 to positive infinity. So that asymptote in the graph is a separator, and the turning point in the graph is a separator between those intervals. Okay, and those separators are what we want to be able to find, because those, again, those are distinguishing between where we're increasing or decreasing. If we have an entire graph that's increasing or decreasing, we really don't have any work to do to find these intervals. But as soon as we have different behavior in our graph, we want to be able to figure out these critical numbers here that separate the behaviors. And so we're going to call those, again, critical numbers. The critical numbers, they are separating, they separate our increasing or decreasing intervals for functions. They are the x values where our function, again, is going to have a slope that is either 0 or undefined. Okay, and again, if our slope is 0 or undefined, that means our derivative is 0 or undefined, because slopes and derivatives are the same thing. So, if I asked you to identify where a function is increasing or decreasing, and presumably we do not have a graph to look at. Now, I don't want you to freak out. I'm not taking your graphs away, right? You're going to be able to use a graphing calculator and Desmos when you take your quizzes, when you take your midterm, but this is the work that you're going to be able, or that you need to do in the event that a calculator would not be available. So like if you're going on to the next level, I don't know what your teacher is going to require of you, so be prepared to do the work, and when you take your midterm, show the work if you want full credit, okay? So how do we find where our graph is increasing or decreasing? Well, we have to find the separators, we have to find the critical numbers. And those critical numbers happen again where our slope is 0 or undefined, which means if I can make my derivative 0 or make my derivative undefined, I can figure out where those critical numbers are. So if we have a function and we want to find where it's increasing or decreasing, and we did not have access to the graph, then we're going to find its derivative. So we're going to start by finding f prime of x. And then we're going to find the critical numbers. So the critical numbers, again, make our slope, our derivative, 0 or undefined. So we don't know where is f prime of x going to equal 0, and where is f prime of x going to be undefined. Okay, if we find those critical numbers, then again we know the separators. So if I knew 2, then I just got to figure out, okay, that I know that that's either 0 or undefined there, what's happening before that and what's happening after that. And so what we're going to do once we find our critical number or critical numbers is we'll put them on a number line, and we're going to then test numbers that are before, between, after critical numbers to figure out if we're increasing or decreasing. So how are we going to know once we test our number if we're increasing? So if we plug into so we get some critical number, okay, let's say our critical number like we had up there was -2. We test something over here to the before it or to the left of it, test something over here after it to the right of it, so maybe we test like -3 and maybe we test -1, right? If we test this, what we want to do is plug it into the derivative function, because if we get something that's greater than 0 would be positive, so that means the slope is positive. If the slope is positive, that means our function has to be increasing. So in the same way we said if the function was increasing, the slope would have to be positive. If the slope is positive, we know our function is increasing. So we're going to test a number, making a big mess here. Before, between, after critical numbers, if we plug those test numbers into our derivative function, when we get something bigger than 0, again, that indicates a positive slope, which means our function, which is what we're trying to identify behavior of, is increasing. So greater than 0 means positive. If we plug into our derivative function and we get something less than 0, that would be negative. So if our derivative is negative, that means our function would have to be decreasing. And we said the reverse of that several times. So we said if our function's decreasing, then our derivative would be negative. Now just in reverse. If the derivative is negative, then the function has to be decreasing. So these are the steps we're going to take. Find the derivative, find the critical numbers, which are the values of x that are going to make our derivative either 0 or undefined. And then we make a number line with those critical numbers, and then we're testing before, in between, and after to see the behavior. Positive tests lead to increasing intervals of graph, and negative tests lead to decreasing intervals of graphs. Okay, so let's try this out. Let's look at a few examples. I have a mixture here, so I've got a rational function, a polynomial function, a radical function, and then a word problem, probably your most favorite thing, right? So let's try it out. We're going to find the critical numbers and decide where each of these functions is increasing or decreasing. So if I want to do this, and I presumably did not have access to a graph, which we'll use to verify our work, but this is the work you're going to be required to do, okay? We're going to start by finding the derivative, so f prime of x. Well, to find this derivative, I'm going to need to use my quotient rule. So I'm going to call this f, call this g. My quotient rule is f prime g minus fg prime over g squared. So in this case, f prime, the derivative of x minus 1 would just be 1, times g, which is x plus 1, minus f, which is x minus 1, times g prime, which is just 1, all divided by g squared, so x plus 1 squared. Alright, so let's clean that up a little bit. Well, multiplying by 1 is not going to change the x plus 1, and I'm going to distribute the negative here. Again, multiplying by 1, not going to do anything, so we're going to have a negative x and a positive 1, and g is still squared on the bottom. So ultimately, f prime of x, our derivative is going to be, let's see, x and negative x, those are going to cancel, so 1 and 1 makes 2. So it's going to be 2 over x plus 1 squared. So there's a function that represents the slope of our curve at any point, okay? So if I can figure out where our slope is 0 or where our slope is undefined, those are the separators in our intervals that are increasing or decreasing. So let's, after we find our derivative, figure out where it's equal to 0 and where it's undefined. So first, to find my critical numbers, okay, where is f prime of x equal to 0? That's going to be one way to find critical numbers. Find where the derivative is equal to 0. So I'm going to take my derivative, 2 over x plus 1 squared, make an equation set equal to 0, and see if I can solve this equation. Well, if I'm trying to find places where this fraction is equal to 0, technically that's 0 over 1. There's a couple ways to look at doing this. It's not going to be possible because there's no variable in the numerator here, but I like to make a fraction equal to a fraction. If I make a proportion, then I can cross multiply. So 0 times my binomial is 0, and then 2 times 1 is going to be 2, and clearly that can't happen. So it is not going to be possible for our derivative to be equal to 0. So that doesn't produce any critical numbers. That's okay. We can also get a critical number if our derivative is undefined. And does that happen? So if we're looking at our derivative, 2 over x plus 1 squared, it's going to be undefined at x equals negative 1, because a negative 1 plugged into our denominator here is going to make a 0 in that denominator, and 0 in the bottom of the fraction is undefined. Okay, so in this process, we have identified one critical number. So x equals 1 is our critical number. So we have one separator. So we have one, again, separator in the behaviors. So we need to figure out what's going on before that place and after that place. So at x equals negative 1, our graph is undefined. There's some discontinuity there. But before that, it's either increasing or decreasing. And after that, it's either increasing or decreasing. So let's make a little number line. And we're going to put our critical number on that number line. So the critical number we're looking at is negative 1. I need to figure out, again, what's happening before that critical number. So I'm going to pick something over here, before or left of or less than negative 1, like negative 2. And then I got to figure out what's going on over here. So after or greater than or to the right of negative 1, which I can pick anything. I usually just pick the next consecutive number. And those two test numbers have to get plugged into our derivative function because I want to know what's happening with the slope there. So if I find f prime of negative 2, I'd be looking at 2 over negative 2 plus 1 squared. So negative 2 plus 1 is negative 1. Negative 1 squared is 1. 2 divided by 1 is going to be 2. That's a positive result. So that means before this critical number, our graph is positive. That positive result means our slope is positive. That means f of x is increasing. Okay? Now I want to find f prime of 0. So 2 over 0 plus 1 squared. That's 2 over 1, which again is a positive result. So after that critical number, again, I have positive slopes. Positive slopes mean my function is increasing. So almost all of my graph is increasing, but we can't say from negative infinity to infinity because we have a discontinuity happening here. So if I was going to answer this one, I would say that this function is increasing from negative infinity up to my critical number, and then after my critical number from, I need to scoot this over or write a little smaller. How about this? Increasing from negative infinity up to my critical number, and then again from that critical number to positive infinity. So everywhere except for at that critical number, this function is increasing. So if you're asked to find the critical number, which you're going to have to do, this would be your answer for that. And then where is the graph increasing or decreasing, and this would be the answer for that. This is no decreasing intervals for this function. Now, this is work we need to be able to do, and again, when you get to your next class, I don't know what the instructor is going to allow or not allow. This is the work we can do to find where a graph is increasing or decreasing, but it's super easy if we actually just had the graph. So you're going to verify your work by looking at your picture. So if we were to graph x minus 1 over x plus 1, what we said is our critical number is at x equals negative 1, and that's where we have a discontinuity in the graph. That's where we said our derivative is going to be undefined. Makes sense. We can't get any slope there because we have no graph there. Now if we look before that critical number, we can see a branch that's increasing, and if we look after that critical number, we see a branch that's increasing, which is precisely what we said here. Okay, so this is the work that leads us to that same concept graphically. Okay? Alright, let's try this again with a polynomial function. I like these a little better than the rationals. I actually basically know the behavior, but let's go through the work. So again, I want to find my derivative. Super easy when these are polynomials. I'm going to use our power rule 3 times here. So the derivative for x cubed is going to be 3x squared, minus the derivative for 3x squared would be 6x. Remember, we're multiplying by the exponent and subtracting 1 from that exponent. And then the derivative of 3x is just going to be 3. So there it is. Don't have to do any fanciness like I did up here. I have my derivative. Now I need to figure out my critical numbers, which would be, where is my derivative equal to 0? So let's do that one first. Let's figure out where 3x squared minus 6x plus 3 is equal to 0. So there's a few different ways you can solve this equation. If you wanted to use your quadratic formula, you could. I would not do that because this is going to be factorable. But actually, I'm going to divide the 3 out of this equation first, since this is a legal move, right? Divide everything by 3. I'm really going to end up solving x squared minus 2x plus 1 equal to 0. And there are factors of 1 that make negative 2. So this factors into x minus 1, which means our solution is going to be 1. So we have one critical number here, because at x equals 1, our derivative is 0. That means we have a turning point in this graph. And that should make sense. Think about what's happening with a quadratic. That's a parabola, and this parabola I know opens up. So we have some parabola that opens up. What we're saying is the turning point happens at x equals 1. So I already know that before that the graph is decreasing, and then after that it's increasing based on the behavior of a quadratic function. But just so we can go through the work and you can see it. So there's where our derivative is equal to 0. You can also find a critical number by finding where your derivative is undefined. But if I tried to figure out where my derivative was undefined, it can't happen. So I can't make a polynomial undefined. A polynomial is defined everywhere. Polynomials go left and right forever. I can take whatever I want as an x value, plug it in, and multiply it by 6 and square. There are no restrictions here. So restrictions will happen with fractions, with radicals, or anytime, there's something we can't do, like I can't have a 0 in the bottom of a fraction. I can't take the square root of something that's negative. That's when you have the opportunity for your derivative to be undefined. But if it's a polynomial, this is not possible. Oops, I can spell. Not possible. Polynomials are defined everywhere. They have domains from negative infinity to infinity. So again, we have one critical number right here. So that is going to be our critical number. I should have put that over here too. Okay, so I'm going to make a number line with my critical number, which is positive 1 this time. So I know that's my turning point. I just got to figure out what's happening before and what's happening after. So before 1, maybe I plug in, let's say 0, and then after 1 I could plug in or test a 2. So into my derivative function, find f prime of 0. So f prime of 0 means we're looking at 3 times 0 squared minus 6 times 0, and then plus 3, so we end up with positive 3. And again, positive means we're increasing. Find f prime of 2. So 3 times 2 squared minus 6 times 2 plus 3. And what did I do? Oh, nothing. Keep going. Okay, sorry. So 2 squared is going to be 4. 4 times 3 is going to be 12. And then we're going to subtract 12 here, plus 3. So we end up with a 3 again. Again means positive. And so I think I said something earlier that made sense in my head, but hopefully we're disregarding. Okay, so we're increasing here too. I said I knew the behavior of this parabola, but I forgot that the parabola is not really what we're looking at. We're looking at this cubic function up here. Okay, so I have one critical number where my slope is going to be 0, and then before that we're increasing, after that we're increasing. So I would say that this graph, again, is going to be increasing from negative infinity up to 1, and then again from 1 to positive infinity, just not at 1 because the slope is going to be 0 there. So let's go ahead and confirm with the graph of our original function. That's what we're trying to find the behavior of. We're just using the derivative to do it. So x to the third minus 3x squared plus 3x is a cubic function that looks like this. And let's put x equals 1 in here. That's the place we're looking. Yeah, we have an inflection point happening there. We're changing concavity, and that's something we're going to talk about later if you have no idea what I just said. But, can't quite. There we go. So that's the point that we're trying to look at. Okay, right there we would have a slope that is 0. That's our critical number. But notice we're increasing all the way through. So before that point we're increasing. After that point we're increasing. But when we get to that critical number, when we get to that inflection point in this one, our slope actually is completely flat, slope of 0. So graphically, the work we have done here makes sense. All right, let's try another. This time we have a radical function, and I want to find the derivative, but I don't want to find the derivative of the radical, so I'm going to put this in rational exponential form, make it a power function so I can use my power rule. So this is the same as x squared minus 4. So the cube root of x squared minus 4 squared is the same as x squared minus 4 to the 2/3 power. Now I can find my derivative, f prime of x, using my power rule. So I'm going to multiply by my exponent, leave this inner function alone, subtract 1 from my exponent. So 2/3 minus 3/3 would be negative 1/3. And then multiply by the derivative of my inner function. So the derivative of x squared minus 4 would just be a 2x. And then because I'm going to be doing some work with this, let me write this in a more manageable way. So this is 2x technically over 1 here, right? So that's going to go to the top of my fraction, so that 2x times that 2 is going to give me a 4x in that numerator. And then in my denominator, I'm going to have that 3. And then this is going to go to my denominator as well because it has a negative exponent. And so that's going to be x squared minus 4 to the positive 1/3 on the bottom, which would be a cube root of that x squared minus 4 to the first power. Alright, so there's the cleaned up version of my derivative. Now what I need to know are the critical numbers. Where is this derivative going to be equal to 0? Where is this derivative going to be undefined? So let's start with, where is f prime of x equal to 0? Alright, so let's take 4x over 3 times the cube root of x squared minus 4 and try to figure out where it's equal to 0. Where again I'm going to make that 0 over 1 to make a proportion here. So that's going to 0 out, and that's going to make a 4x. Right, if we're trying to find where a fraction is going to be equal to 0, we have to basically know where the numerator is going to be equal to 0. That's why it couldn't happen in this other one, because the numerator of 2 could not be equal to 0. Okay. So in this case, though, we have a variable. 4x can be equal to 0. If I divide the 4 over, I find 0 is a critical number. Okay. Now in this one, not only do we have a critical number where our derivative is equal to 0, but we can also find where our derivative is undefined. Because we have a fraction, we have a restriction. So we're going to get more than one critical number here. So when is 4x over 3 times the cube root of x squared minus 4, where is that going to be undefined? It's going to be undefined when our denominator is equal to 0. So let's do this. Is undefined if the denominator, in this case 3 times the cube root of x squared minus 4, is equal to 0. So we got where the numerator is equal to 0, that makes our function 0, so that's one critical number. Now, undefined, again, when the denominator is equal to 0, so we're going to do a little work to figure that out. If I divide the 3 over, I would still have the cube root of x squared minus 4 equal to 0. I'm going to cube both sides to get rid of my, I need another color. Cube both sides to get rid of my cube root, and that's going to get me x squared minus 4 still equal to 0. Add 4 to both sides, so x squared equals 4, and then take the square root of both sides, and positive and negative 2 squared both make 4, so x equals positive or negative 2. So I actually get 3 critical numbers here. At x equals 0, our slope is 0, and at x equals 2 and negative 2, our slope is undefined. So I have to test several things here. Let's make our number line. Okay, so I have negative 2, 0, and positive 2 on this number line as critical numbers. So at those places, our slope is 0 or undefined. But again, I have to figure out what's happening here, what's happening in between here, what's happening in between here, and what's happening over here. So anything before, after, or in between, we have to determine the behavior of. So I actually have to take 4 test numbers here. So something after negative 2, like negative 3, something between, like negative 1, something between here, like positive 1, and something after here, like positive 3. And all of these are going to go into our derivative function. So let's find f prime of negative 3. That would be 4 times negative 3 over 3 times the cube root of negative 3 squared minus 4. Goodness. Okay, so that's a negative 12 over negative 3 squared is 9. 9 minus 4 is 5. Cube root of 5 is going to be positive times 3, whatever. So positive result on the bottom. I don't even really care what the result is because I know a negative divided by a positive makes a negative. So we're going to be negative out here, which means we will be decreasing. And then I'm going to pick negative 1, I said. So f prime of negative 1. And the same thing. Nope, not the same thing. 3 times the cube root. I mean, same process, but not the same result. Because in our cube root here, we have a negative 1 squared, which is a 1, but 1 minus 4 is a negative 3, and the cube root of that negative will be negative. Negative times 3 will be negative, so I know I get a negative here, and I get a negative on the top. Negative 4 on the top, negative on the bottom, so it's going to be a positive result. Again, I'm not so concerned with what the actual result is. I just need to know if it's positive or negative. Now that I know it's going to be positive here, I know that this interval of graph will be increasing. Now when I go to plug in positive 1 and positive 3, what is going to be the difference? Let me just shortcut my work a little bit. If I change this to a positive, this to a positive, and this to a positive, well, then this becomes a positive 12, but on the bottom here I get the same positive, so this becomes positive. And so this is going to be increasing. And then if I make this a positive 1, and this a positive 1, and this a positive 1, then, let's see, 4 times positive 1 on the top will still be positive, and sorry, I was just double checking my other work. On the bottom there, the positive 1 squared is 1 minus 4 is still going to be a negative 3 under that cube root, so we still get a negative denominator, which means we'll still be negative here. So negative here means decreasing. And if you're doing that part and you're, don't want to do the math, then don't. Just put your function in. So we had 4x over 3 times the cube root. This takes a minute, especially if you have fat fingers. Cube root of x squared, and then minus 4. Okay, so here, now if you have your function and you just want to plug the numbers in, so let's just put the negative 3 in there, and let's put the negative 3 in there, and then again you can see that I got a negative result, and then I can just swap this negative 3 out with a negative 1, and I can see my positive result, and then I can get rid of this negative here, and I can see my at positive 1. Uh-oh. I goofed. Oh yeah, I did this out of order. Shoot! Good thing I was double checking my work. See, this is a good thing to use a calculator. So I did the right work on the side, but I definitely labeled this wrong. So f of 3 being positive, for some reason I labeled that on 1. So this is going to be a negative here, which means decreasing, and this was a positive here, which was increasing. So maybe don't do like I did and try to shortcut your work, because that just made a mess of what I was doing. Okay? So you can learn from me what to do and learn from me what not to do. Maybe you just use your calculator, it's easier. Okay, so now that I have that, then I'll go and put my positive 3 in, so let me just take this out. And boom, positive results. Okay, so now I have increasing, decreasing, and that rotation happening a couple of times. So if I was going to answer this, I got my critical numbers, and I would say this function is increasing over 2 intervals. So increasing happens here, and it happens here. So we're going to say it's increasing from negative 2 to 0, and from 2 to infinity. And then decreasing intervals were over here and here. And I should have put an arrow on this one. Okay, so we're going to say this graph is decreasing from negative infinity up to negative 2, and then between 0 and 2. Okay, so that's a lot of algebra, but luckily we can confirm all of this. So this increasing and decreasing behavior is in reference to our original function. Let's go ahead and put that original function in. The cube root, I guess I shouldn't have deleted what I had there. So the cube root of x squared minus 4, and that was all squared. So here's our original function, and we said critical numbers were happening at, negative 2, 0, and 2. So at negative 2, I'm going to have undefined, that spike in the graph there is not a defined place for us to find slope. Same thing happening at positive 2. And over here at 0, we're going to have that turning point, that flat slope. So the critical numbers that I got there, I can see those on the graph now. And if I was reading this behavior, we are over here decreasing and then increasing till we get there, then we're 0, then we're decreasing, and then increasing. So the same behaviors that I said here, those are happening on the graph. This is just the work we can do to get to those behaviors. Alright, it's crazy work, but you're in calculus, okay? So have fun. No. Alright, last one. Just to bring some connection to this and our business application. So the costs and revenue for a toy distributor manufacturing X number of toys are given by the following functions. So C of X here representing our costs, and R of X here representing our revenue. And this is for, it says X greater than or equal to 0, which makes sense. X's are the number of toys. We're not going to have a negative number of toys. Okay. So we want to, in this question, figure out the interval or intervals over which our profit is increasing. That's definitely something that a company would want to know. But they didn't give us a profit function here, although we know from previous experience, if we wanted to find our profits, we would take all the money we spend, which would be our costs, and then we would subtract out all of the revenue, that's the money that we bring in. Just kidding. Backwards. All the money we bring in, that's our revenue. And then we're going to pay our bills. Let's subtract out those costs. And the revenue minus the cost. Right after we bring all that money in, subtract out all the bills we have to pay, everything that's left over becomes our profit. So in this case, we're going to say P of x is going to equal, let's see, revenue is 7.2x minus 0.001x squared. From that, we want to subtract costs, which are 2.4x minus 0.0002x squared. And so this becomes, let's see, 7.2x minus 0.001x squared minus 2.4x, and then plus 0.0002x squared. And then we'll combine like terms. So 7.2, let's not make a silly mistake this late in the game. 7.2 minus 2.4 is going to be 4.8. So we have 4.8x. And then if I have negative 0.001 and a positive 0.00, I said decimal point, 0, come on, fat finger, you can do it. 3 zeros and then a 2, that makes negative 0.0008. Negative 0.0008x squared. Make sure I got that in there correctly. Yep, okay. So here is our profit equation. Now, if I want to find, again, where our profit is increasing, I want to find the derivative and the critical numbers. So now I have P of x. Let's find P prime of x. So this will be an easy one. We can use our power rule. The derivative for 4.8x will just be 4.8 minus, here we're going to multiply by 2, so that's going to turn the 8 to a 16. So 0.0016 x to the first becomes our profit function. So where is this profit going to be increasing? Let's figure out our critical numbers. Sorry. I keep trying to look at my stuff. Okay, so we want to know critical numbers. What's going to make our profit function equal 0? That won't be too bad. What makes 4.8 minus 0.0016x equal 0? Well, we're going to first subtract over, well, I guess I could solve it the other way. I could subtract 4.8, or I could just add over, let's do that. I don't know why. 0.0016x, I just added that over. And then divide. So 4.8 is going to be divided by 0.0016, and we get 3,000. So at x equals 3,000, we have a slope of 0, which means, again, that's going to be a separator between increasing and decreasing, or maybe it's increasing, whatever, but it's going to be some sort of separator in these intervals. And then if we were trying to figure out where P of x was undefined, that's not going to be possible. Again, P of x is, gosh darn, I'm so sorry for the scrolling. P of x is a linear function. This is defined for all values of x. It goes left and right forever without any restriction. So P of x being undefined is not possible. So we don't have to worry about that. So we have just one critical number right here. Okay, so we're going to make our number line. Squeeze this in because we're running out of space. Maybe you write smaller than me. 3,000. What's happening before that? What's happening after that? That's what we got to figure out. So I'm going to pick something before 3,000. Back to my consistency with color. So 3,000's here. I'm going to pick something before. And normally I go consecutively right before, but I don't want to plug that giant number in when 0 is before 3,000. So I'm going to plug in 0. And then I'm going to plug in 3001. Okay, so these are going to get plugged into my derivative function. P prime of 0 would be 4.8. And hopefully you can just see that, but 4.8 minus 0.0016 times 0, right? That makes 4.8, which is going to be positive. So we're going to be increasing here. And then 3001. It's going to be negative, I can already tell, but let's use the calculator. So we're going to have 4.8 minus 0.0016 multiplied by 3,000, so I can see that's going to be a big negative there. 4.8 minus 3,000, just kidding, 0.0016 times 3,000. and oh, sorry, not 3,000. 3,001. Like 0, duh, that's what we calculated. So then we get negative 0.0016. Again, it doesn't really matter, it just matters that it's negative because that tells us that we're decreasing there. So we don't want to be producing, if you're this toy company, you don't want to be producing more than 3,000 of these toys, or manufacturing more than 3,000 of the toys, because after that your profits start to decrease. Now you're still, I guess, technically making profits, but we want those profits to be going up, not going down. So our profits are increasing. Let's try to fit this in here. Profits are increasing. Now, we could, if there was no context, I would say that we're just increasing here. Now, again, out of context, this would be from negative infinity up to 3,000. But remember, we're looking at toys, and we're not going to have anything less than or equal to, or less than 0. I guess we could technically, well, it says not to be equal to 0, but so greater than 0, but less than 3,000. So if you were just to write the increasing interval, you would say from 0 to 3,000 in parentheses. But if we're doing this in words, it wouldn't make a lot of sense to say it that way. Increasing over the interval from 0 to 3,000. And then that's 300. Okay, so you could say it like this, but I think I would prefer, and I'm just running out of space, so I'm not going to write it, but I think I would prefer a sentence like profits are increasing when between 0 and 3,000 toys are manufactured. That would make a little more sense in the context. And you would say strictly between 0 and 3,000 because we don't want to include the 0 or the 3,000. We're not including the 0 here. Oh, actually we are including the 0. I didn't highlight it, so I didn't see it. So from 0 to 3,000 including the 0. So if they manufacture 0 toys or any number of toys less than 3,000 toys, then their profits are increasing. Okay, now just because we should, let's be thorough and put in our original function. And I'm going to just type the whole thing in there and make sure I didn't goof up anything. So 7.2x and minus 0.001x squared, and from that we wanted to subtract 2.4x minus 0.002x squared. Okay, so that's our profit function, and at 3,000 I gotta do a little bit of zooming here. Nope. Okay, where did I type something in wrong? Let's put this in. Don't mind me. Oh yeah, I typed something wrong somewhere. 2.4x point. Can't see. Oh, I missed a 0. See? Jeez, guys. You probably like saw me do it. There we go. Because at 3,000 we should see a turning point in this graph, which is going to happen here. There we go. So at 3,000 we can see our slope zero out, and we can see that before 3,000 we are increasing, and then after 3,000 we are decreasing. So again, the graph is there so that we can confirm that the work that we've done by hand, it's just super helpful if you're like me, making little mistakes all over the place. Hopefully they didn't inhibit your learning in this case, but there we have it. So again, I'm not taking away your calculator when you take your midterm exam. Obviously you have it when you take your quizzes, but this is the work that is going to be expected of you when you take your midterm. I'm going to require this work for full credit on questions like these. And then you especially need to be careful when you go to the next class, because I don't know, if your next professor is going to require you to use, or going to allow you to use a calculator and everything, or require you to do everything by hand, okay? So hopefully you've got enough. Hopefully I didn't make too big of a mess of this, but if you have any questions, by all means reach out. Until next time, take care.